Hello, good day everyone. This is our presentation on the Preliminary Design Review Outline or PDR for the Cansat 2021 competition. We are Team Blue Star and we are team number 5. Here is our presentation outline. We will be talking about systems overview, sensor subsystem design, descent control design, communication and data handling subsystem design, electrical power subsystem design, ground control system design, Cansat integration and test, and management. Our team organization is as follows. Brian Emilio Piñón Ruiz is our team leader. Eloy Normando Márquez González is our faculty advisor. Adriana Emily Corral Valenzuela is in charge of mechanical subsystems and is our alternate team leader. Marcos Loya Flores is in charge of electrical and computer subsystems. Finally, Ivan Alejandro Flores Otero is our aeronautical subsystem sophomore. We start with our systems overview. Mission summary. Design a Cansat that shall consist of a container and 2 auto-rotating maple seed science payloads. The container shall carry electronics to release the maple seed science payloads and relay data from the payload to a ground station. The Cansat shall be launched to an altitude ranging 670 meters to 725 meters above the launch site and deployed near apogee. The Cansat container must protect the science payloads from damage during the launch and deployment. Once the Cansat is deployed from the rocket, it shall descend using a parachute at a descent rate of 15 meters per second. At 500 meters, the container shall release 1 auto-rotating maple seed science payload. At 400 meters, the container shall release the second auto-rotating maple seed science payload. The container shall relay all telemetry sent from the science payloads until the container lands. The container shall also incorporate its own telemetry along with the maple seed science payload telemetry. The container shall transmit using the team number as its net ID. The auto-rotating maple seed science payloads shall descend after being released and spin rapidly enough so its descent rate is less than 20 meters per second. The science payload shall transmit telemetry 1 time per second and include air pressure and air temperature. The science payloads shall transmit for 5 minutes after being released and use the team number plus 5 as its net ID number. Now let's review our system requirement summary. We're going to go through every requirement right now, and later on we specify a few of them for different applications, but you can come back to this list and check as needed. So for requirement number 1, we have that the total mass of the Cansat science payloads and container shall be 600 grams plus or minus 10 grams. 2. Cansat shall fit in a cylindrical envelope of 125 millimeters diameter times 400 millimeters length. Tolerances are to be included to facilitate container deployment from the rocket fairing. 3. The container shall not have any sharp edges to cause it to get stuck in the rocket payload section, which is made of cardboard. 4. The container shall be fluorescent color, pink, red, or orange. 5. The container shall be solid and fully enclose the science payloads. Small holes to allow access to turn on the science payloads is allowed. The end of the container where the payload deploys must be open. 6. The rocket airframe shall not be used to restrain any deployable parts of the Cansat. 7. The rocket airframe shall not be used as a part of the Cansat operations. 8. The container parachute shall not be enclosed in the container structure. It shall be external and attached to the container so that it opens immediately when deployed from the rocket. 9. The parachutes shall be fluorescent, pink or orange. 10. The descent rate of the Cansat container and science payload shall be 15 meters per second plus or minus 5 meters per second. 11. All structures shall be built to survive 15 gravitational units of launch acceleration. 12. All structures shall be built to survive 30 Gs of shock. 13. All electronics shall be hard mounted using proper mounts such as stand-ups, screws, or high-performance adhesives. 14. All mechanisms shall be capable of maintaining their configuration or states under all forces of the environmental tests laid down in section 3.5. 15. Mechanisms shall not use pyrotechnics or chemicals. 16. Mechanisms that use heat, for example nichrome wire, shall not be exposed to the outside environment to reduce potential risk of setting vegetation on fire. 17. Both the container and payloads shall be labeled with the team contact information, including email addresses. 18. Cost of the Cansat shall be under $1,000. Ground support and analysis tools are not included in the cost. 19. XB radios shall be used for telemetry. 2.4 GHz series radios are allowed. 900 MHz XB radios are also allowed. 20. XB radios shall have their net ID, PAN ID set to their team number. 21. XB radios shall not be used broadcast mode. 22. The science payload shall descend spinning passively like a maple seed with no propulsion. 23. The science payload shall have a maximum descent rate of 20 meters per second. 24. The wing of the science payload shall be colored fluorescent, orange, pink, or green. 25. The science payload shall measure altitude using an air pressure sensor. 26. The science payload shall measure air temperature. 27. The science payload shall measure rotation rate as it descends. 28. The science payload shall transmit all sensor data once per second. 29. The science payload telemetry shall be transmitted to the container only. 30. The science payload shall have their net ID, PAN ID set to their team number plus 5. If team number is 1000, sensor payload net ID is 1005. 31. The container shall include electronics to receive sensor payload telemetry. 32. The container shall include electronics and mechanisms to release the science payloads. 33. The container shall include a GPS sensor to track its position. 34. The container shall include a pressure sensor to measure altitude. 35. The container shall measure its battery voltage. 36. The container shall transmit its telemetry and the payload telemetry received once per second in the format described in the telemetry requirements section. 37. The container shall stop transmitting telemetry when it lands. 38. The container and science payloads must include an easily accessible power switch that can be accessed without disassembling the Cansat and science payloads into the stowed configuration. 39. The container must include a power indicator such as LED or sound generating device that can be easily seen or heard without disassembling the Cansat and in the stowed state. 40. An audio beacon is required for the container. It may be powered after the landing or operate continuously. 41. The audio beacon must have a minimum sound pressure level of 92 decibels unobstructed. 42. Battery source may be alkaline, NiCad, NiMH, or lithium. Lithium polymer batteries are not allowed. Lithium cells must be manufactured with a metal package similar to 18650 cells. Coin cells are allowed. 44. An easily accessible battery compartment must be included, allowing batteries to be installed or removed in less than a minute and not require a total disassembly of the Cansat. 45. Spring contacts shall not be used for making electrical connections to batteries. Shock forces can cause momentary disconnects. 46. The Cansat must operate during the environmental test laid down in section 3.5. 47. The Cansat shall operate for a minimum of 2 hours when integrated to the rocket. 48. The flight software shall maintain a count of packets transmitted, which shall increment with each packet transmission throughout the mission. The value shall be maintained throughout processor resets. 49. The container must maintain mission time throughout the whole mission, even with the processor resets or momentary power loss. 50. The container shall have its time set to UTC time to within 5 seconds before launch. 51. The container flight software shall support simulated flight mode where the ground station sends air pressure values at a 1-second interval using a provided flight profile CSV file. 52. In simulation mode, the flight software shall use the radio uplink pressure values in place of the pressure sensor for determining the container altitude. 53. The container flight software shall only enter simulation mode after it receives the simulation enable and simulation activate commands. 54. The ground station shall command the Cansat to start transmitting telemetry prior to launch. 55. The ground station shall generate CSV files of all sensor data as specified in the telemetry requirements section. 56. Telemetry shall include mission time with 1 second or better resolution. Mission time shall be maintained in the event of a processor reset during the launch and mission. 57. Configuration states such as, if commanded to transmit telemetry, shall be maintained in the event of a processor reset during launch and mission. 58. Each team will develop its own ground station taking into account the restrictions and the health security measures due to the COVID-19 pandemic. 59. All telemetry shall be displayed in real time during descent on the ground station. 60. All telemetry shall be displayed in engine units, meters, meters per second, Celsius, etc. 61. Teams shall plot its telemetry data filed in real time during the flight. 62. The ground station shall include one laptop computer with a minimum of 2 hours of battery operation, XB radio, and handheld antenna. 63. The ground station must be portable so the team can be positioned in the ground station operation site along the flight line. AC power will be not available at the ground station operation site. 64. The ground station software shall be able to command the container to operate in simulation mode by sending 2 commands, simulation enable and simulation activate. 65. When it's simulation mode, the ground station shall transmit pressure data from CSV file provided by the competition at a 1 Hz interval to the container. 66. The science payloads shall not transmit telemetry during the launch, and the container shall command the science payloads to begin telemetry transmission upon release from the container. As you may have noticed, there are a few requirements marked in red. These requirements were implemented to the summary by our team. Now let's review system level Cansat configuration, trade, and selection. This is our option 1, and you can see a little sketch there on the right. It is proposed that the mechanism unfolds the wings by a means of a motor. It is proposed that the whole structure is made of plastic. The parachute would be made of nylon and have a hemispherical shape. The container would have a square shape for easier manufacturing. The hinges would be made of aluminum, and aluminum is also proposed for the central aerodynamic profile. And here we have option 2. The hinges would be made of iron. The parachute would be made of nylon and have a hemispherical shape. The container would have a cylindrical shape. An electronic lock mechanism is suggested. It is proposed that the whole structure is made out of carbon fiber. Carbon fiber is preferred for the central aerodynamic profile in this case. Well, as you can see on this table, we selected option 2. The concept of this Cansat was chosen based on a brainstorm where we exposed different materials, as well as different shapes, and it helped us to choose the most appropriate one, seeking to meet the needs of requirements for the mission. The shape chosen for the Cansat will be cylindrical, since among the benefits we can find its ease of construction, the dispersion of kinetic energy to avoid any collision, and the easy handling of the space where the payload will be deposited. Sensor subsystem design. Okay, so here we have different models of type sensors as well as their function. For example, the pressure and temperature sensors, which are used to measure air temperature and air pressure. We have a GPS to get the payload coordinates. We have a voltage sensor to measure the battery voltage, airspeed sensor, particulate dust sensor, and a camera used to record video from the camera. The requirements that apply for these subsystems are requirements number 1, 2, 14, 15, 18, 22, 23, 24, 25, 26, and 27. Now let's move on to descent control design. Here we have the overview. For phase 1, the Cansat will separate from the rocket by 670 to 725 meters. Phase 2, the Cansat will descend using a parachute at a descent rate of 20 meters per second with passively control plus or minus 5 meters per second. Phase 3, at 450 meters plus or minus 10 meters, the payload will be released from the container. Phase 4, after the payload is released from the container, it will glide at above 100 meters for 1 minute within a radius of 250 meters with active control. It will glide according to the reference point. Phase 5. After gliding for a minute, it will ground with the parachute at a speed of 10 meters per second with passively control plus or minus 5 meters per second. Components. Here we show the component and the material used to make it. The glider wing support structure would be 3D printed. Hinges made out of iron. Wing body, foam board. Parachute, ripstop nylon. Parachute cord, nylon shroud. And the requirements that apply for descent control are requirements 1, 3, 4, 7, 8, 9, 11, and 13. Communication and data handling, CDH, subsystem design. We have a chart here for the CDH overview. We have Arduino Nano Function Real-Time Clock Keeper. Teensy 3.6 is the data collector and data processor. XB900HP Pro transmits and receives data. Micro SD card, backup data storage, onboard payload. And the CDH requirements are requirement number 19, 20, 21, 29, 60, 61, and 62. Electrical Power Subsystem, EPS design. The components used in this section would be battery. It is used as a power source for the components for at least 2 hours. P-channel MOSFET protects the circuit from a reverse polarity. Switch diverts and interrupts the circuit flow from battery to electronic system. Power indicator that indicates if the system obtains energy. Energy distribution guarantee that the other electronic will receive the correct voltage and current levels for the entire time of mission. Microcontrollers, controller on which the code resides to interface of the rest of the components. And sensors used to collect information regarding the temperature, air pressure, and others. Camera records a video in a point to where the coordinates provided for the duration of the glide time. Memory collects the data obtained during the flight. Radio allows communication between the Cansat and the ground station. Audio beacon, it allows to find the scientific vehicle easily at the end of the mission. Electric motors, they are responsible for activating the decoupling mechanisms. Here we have a chart for the EPS overview, starting with battery, followed by MOSFET, switch, power indicator, and energy distribution. The latter divides into 2 sections. 5 volts includes terminator and electric motors, and 3.5 volts, which is microcontrollers, sensors, memory, radio, and camera. The requirements that apply for the EPS section are 15, 49, 50, 53, 54, 55, and 57. Ground Control System Design, CGS. GCS Overview. Here we have a chart that explains the data flow. The CGS requirements are shown in requirements number 17, 18, 19, 20, 21, and 64 through 63. 56, 57, 58, 59, 60, and 61. Cansat integration and test. Here we have a chart of the Cansat integration and test overview. This one is divided by 3 levels. The first one is the subsystem. It includes sensors, CEDH, EPS, radio communications, and design control. The second one is integrated level, which is communications, deployment, and design testing. And the last one is environmental. It includes drop test, thermal test, vibration test, and fit check. So now we explain a little better each of these points. For sensors, we have the component level, which is test accuracy of sensor readings and test motor response time. For the system level, ensure live data collected by sensors can be transmitted and stored. Verify software can control wing, glider, and parachute deployment. Ensure data transmission starts on command. Verify live data plotting. For the subsystem level, we have multiple sensor data can be measured at the same time. Test camera response to changes from GPS. And others. Test all sensors on the breadboard. Calibrate until rate accuracy is high, and repeat testing. For communication data handling CDH, we have in the component level, check if RTC keeps time in case power disconnection, test if data can be received with XB, test if data is stored in SD card. For the system level, ensure live data transmission can be controlled by FSW, verify data packets are sent in appropriate time intervals. And for subsystem level, we have ensure microcontroller keeps its function in case of power disconnection. Others, GPS real-time clock test, antenna range test, and sensors and controller interfaces test. EPS. For component level, test if voltage is maintained under expected load for 5 volts, 3.3 volts, and 1.8 volts regulator. Ensure battery can run for 3 hours at expected load level. Test if data is stored in SD card. For system level, ensure power requirements are satisfied. Test the system in different external conditions. Subsystem level, ensure all power rails behave in combination. And others, ensure there are no current leakage, ensure each component function properly, and ensure total power sufficient. Radio communications. Component level. Ensure XB sends data by testing with randomly generated data. Test live graph generation with randomly generated data. System level. Verify live data transmission is not affected by external conditions. Ensure data transmission can be actuated by command. Subsystem level. Verify communication occurs and at above the required range. Test data transmission can be stored by generating random data every second. Others. SWR stability test, beam accuracy test. Descent control. Component level. Ensure easy container parachute deployment. Ensure easy glider parachute deployment. System level. Ensure the payload is aerodynamically stable. Ensure the payload descends in a circular pattern. Subsystem level. Flight simulation testing. Ensure wing deployment is not affected by external conditions. And others, drop test the payload in different altitudes. For the integrated level, we have communication, which is communication of XBs, deployment, payload release from container test using mount of fish line method, and payload's parachute opening test using mount of fish line method, descent testing, container parachute test, payload parachute test, and delta wing test. Environmental level, drop test. The payload holding test of the container. Component and battery mounts test. 30 G's chalk durability test of the system. Thermal test. Cansat's temperature durability test at 60 degrees Celsius for 2 hours. Vibration test. This test will be conducted to verify the mounting integrity of all components, mounting connections, structural integrity, and battery connections. Fit check. Checking the Cansat dimensions for the requirements. Management. Now let's talk about the Cansat budget of the hardware. In this table we show a few parts that we need, the price, the quantity, and the total price after the quantity. For example, we have the Arduino Nano, the XBs, the adapters, the mini spy camera, the SD cards. As we can see on this list, we have the price for each of them. As I mentioned before, we have the quantity. For example, the Arduino Nano is $22 and we need 2 of them, so a total price would be $44. and so on for the rest of the components that we need. Here we have the program schedule overview. This is basically a table of our organization as a team. We can see here the assignments that we need to perform, the quantity of days that we have for each one of them, and the dates. We're not going to go into detail through each point, but it's pretty standard. For example, we have, in the other part, we have the team meetings and the preliminary sketches. We have like the first part of it. And now here we can see manufacture PCB, we have acquire selected radio, we have descent test, communication test, mechanism test. This is basically once we already have most of it done. Some of the last assignments we had to complete were, as you can see, review and update PDR, environmental testing, final stage, and all of this taking into account if we would have actually made the Cansat. So this is how we finally arrived to the end of our presentation. Next, we only have the conclusions. This is what we could gather from this experience. During this course, we acquired knowledge which was later applied to the project with the idea of completing a series of objectives, which are shown below. We were not able to complete this project to a maximum level. However, we are very happy with the results of what we could accomplish. It was a rich experience we had as a team, and we look forward of taking advantage of all we learn here in the future. The objectives accomplished are theoretical and conceptual development of the Cansat 2021 project, deep analysis of all the project stakeholders, refinement of all the Cansat 2021 requirements, delivery of the project on the expected date and time. The objectives that were not achieved are real manufacture of the Cansat 2021, in-depth analysis of the mechanisms of the Cansat 2021, and the complete development of all parts of the PDR version 1.1 template. This will be all from our team, and we thank you for your time.